I want to start this lesson off by taking a look at a certain polynomial, x² plus 2x plus 7. If I asked you to factor this polynomial, you'd start off by checking whether the leading coefficient is 1 or not. Since it is indeed 1, you'd begin by looking for factors of 7 that sum up to 2. Listing the factors of 7, we get 1 and 7. That's it. Just that one set of factors. The sum of that set of factors is 8. What now? What can you do at this point? Well, as of right now, you can't do anything. You don't have the tools yet to be able to factor this polynomial. A polynomial like this has a specific title. It's called non-factorable over the integers. It means we won't get integers when it's fully factored. There'll be decimals or fractions. There'll be times when you have to factor lots of polynomials, and you might be wondering, is there an easy way to determine if a trinomial is factorable or not? And the answer is yes, there is. The Factorization Theorem. The trinomial ax² plus bx plus c with integer coefficients a, b, and c can be factored as the product of two binomials with integer coefficients if and only if b² minus 4 times a times c is a perfect square. That unique collection of variables, b² minus 4ac, has a name. It's called the discriminant. While it has a wider range of use later on, our only use for now is to determine if a polynomial in the form of ax² plus bx plus c is factorable over the integers or not. Also of unique interest, notice that the second term includes the a times c that we looked for in the previous lesson to find factors that sum up to b. Let's use the polynomial we used at the start. x² plus 2x plus 7. We'll use the coefficients of the trinomial and place them into the discriminant. We see that a equals 1, b equals 2, c equals 7. Therefore, b² minus 4ac equals 2² minus 4 times 1 times 7. Our goal is to see if this gives us a perfect square. We have 4 minus 4 times 7, which equals 4 minus 28, which equals negative 24. Negative 24 is not a perfect square. Therefore, our trinomial isn't factorable over the integers. Let's try another. 6x² minus 5x minus 4. Using the factorization theorem, we have b² minus 4ac equals negative 5² minus 4 times 6 times negative 4. This equals 25 minus 4 times negative 24 equals 25 minus negative 96, which equals 25 plus 96, which equals 121. Since 121 is a perfect square, 11 squared equals 121, or square root of 121 equals 11, whichever you'd prefer, the trinomial is factorable. Using our previously learned rules, we can find the factors of a times c, which equals negative 24. And the factors that add up to negative 5 are 3 and negative 8. Our trinomial then becomes 6x² plus 3x minus 8x minus 4. Using grouping, we have 3x times 2x plus 1 minus 4 times 2x plus 1, which equals 2x plus 1 times 3x minus 4. Let's work out a couple examples. Number 1. 2x squared plus 3x minus 4. Before we start to look for factors, let's check and see if this trinomial is factorable over the integers. Recall the formula for the factorization theorem, b squared minus 4ac. Using the given coefficients and constant, our discriminant gives 3 squared minus 4 times 2 times negative 4 equals 9 minus 4 times negative 8. This equals 9 minus negative 32, which equals 9 plus 32, which equals 41. 41 is not a perfect square, therefore this trinomial isn't factorable over the integers. Number 2. X squared plus 3x minus 4. This trinomial is almost the same as the first, only that this one has a leading coefficient of 2 instead of 1. Let's use the factorization theorem and check its factorability. Using b squared minus 4ac, we get 3 squared minus 4 times 1 times negative 4. This equals 9 minus 4 times negative 4 equals 9 minus negative 16. This equals 9 plus 16, which equals 25. 25 is in fact a perfect square because the square root of 25 equals 5. So let's go ahead and factor. The leading coefficient is 1, so we need factors of negative 4 that sum to 3. Since c is negative, one of our factors will also be negative. And since b is positive, the smaller factor will be negative. The factors of c are negative 1 and 4, negative 2 and 2. The sums of these factors are 3 and 0. The first set is the correct answer, therefore our trinomial factors into the binomial product of x minus 1 times x plus 4. Look at the difference of these two examples. There was only a slight difference, a difference of 1 on the leading coefficients. But that small difference completely changed the factorability of the trinomial over the integers. Later, when we begin to study equations, we'll learn about a special equation that we can use to completely factor any trinomial, no matter how difficult. Recall back when we first learned to multiply polynomials. We discovered that sometimes patterns appear when the polynomials have certain numbers involved with certain types of polynomials. The same thing happens with factoring polynomials. In the next few lessons, we'll look at some special cases that show up that'll make our work a bit easier.